mentioning your expertise, so that we broadcast that video to the users. As said, this will help generating new research collaborations, presenting your work, sharing your ideas and also publicizing your expertise and skills. Please see the video is of 10 to 15 minutes. We look forward for your positive response.
The webinar will begin shortly.
Us today.
Please remain on
Thank
the
you.
line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line.
Science mobile app currently have 18,000 subscribers in India and also in 12 other countries. We are looking for experts like you who can deliver an expert talk for 15 to 20
The
minutes
webinar
in
will
your
begin
current
shortly.
research area.
Please remain
Or
on
you
the
can also
line.
present your profile so that interested collaborators will approach you for consultancy, research progress, or academic collaboration. Just accept our invitation, so that you broadcast your video in the appropriate groups and also in mobile app with timely notification to all the users. This helps to share the knowledge to the required students, scholars, etc. Prepare the PPT content and recorded video with any screen recorder software or simply send your selfie video mentioning your expertise, so that we broadcast that video to the users. As said, this will help generating new research collaborations, presenting your work, sharing your ideas and also publicizing your expertise and skills. Please see the video is of 10 to 15 minutes. We look forward for your
The
positive
webinar will
response.
begin shortly.
Contact us
Please
today.
remain on the line.
Thank you.
The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line.
Good evening, all. Welcome to another informative webinar from STAR Certification. Today, we are going to hear from our distinguished speaker about robotics. You all would agree that, like work from home, online learning, or spending good amount of screen time, automation too has become new normal in this COVID-19 situation. In recent past also, automation has started disrupting many industries, especially manufacturing, logistics, retail, agriculture, transportation, etc. And moving forward, automation is going to have its more impact on services like finance, customer relationship, healthcare, and even human resource. In nutshell, automation and allied technologies are going to rule the world, and knowing about more these technologies is the need of the hour. Hence, this illuminating session on robotics is being arranged for you today. Before we proceed further, I would also like to take this opportunity to share a few words about STAR certification. Dear friends, STAR certification is a vendor-neutral global certification body based out of California, having our presence globally and offices in US, Australia, and India. Certification offered by STAR are recognized by NICCS, Department of Homeland Security, and we are ANSI accredited member, where ANSI stands for American National Standard Institute. STAR provides certifications in 3 verticals, namely software technology, we call them computer programming language domain as well, cyber security, and disruptive technology. Now let me also give you some detail about more courses and certifications for your reference, which has become certification bywords in industry and in academia. Friends, under disruptive technology domain, most of our certifications are on cutting-edge technologies, and one of them, which is trending, is robotics, highlighted on your screen. As we are about to commence the learning session, here are a few other important information about the webinar. To avoid any unwanted disturbance during the session, all participants are kept on mute mode. In case of any questions regarding views of the speaker or about STAR certification courses, you can post your query in QA session. Alternatively, you can mail to us and we will revert. As a part of the package, all participants will be getting an attendance certificate post this webinar along with other relevant material from STAR certification. Now, to deep dive into the topic of the day, robotics, Dr. S.S. Mantha has joined us from Mumbai. We are glad to have him for the session today. Personally knowing him for over a decade, I had seen him spearheading many initiatives of modernization of education and promoting the industry-relevant courses in academia. Now, let me give a small official introduction about Dr. S.S. Mantha, and later we'll hand over the session to Professor. Dr. Mantha is former chairman of national regulator AICTE and has implemented several e-governments initiatives, and facilitating regulations. Earlier, a professor of robotics, control theory, and AI at VJTI Mumbai, he now occupies the emeritus chair. He has more than 280 publications in national and international journals and conferences, besides authoring 3 books. Presently, he is Chancellor at Keele University and Adjunct Professor at National Institute of Advanced Studies, NIAS, Bengaluru. He is also Chairman of Technical Committee, National Cyber Safety and Security Standards, NCSSS, and IT expert for Government of Maharashtra. With this brief introduction, ladies and gentlemen, I hand over the session to Dr. S.S. Mantha to present his views on robotics. Dr. Mantha, good evening and welcome to the session.
Good evening. Good evening, all the participants as well. What I'll do is take you through a session on robotics to try and understand what the subject is about. Today, almost everybody speaks about robotics, AI, and so on. So therefore, in today's world, almost every application seems to be talking about some kind of automation. And within the industry space, automation has automation is a generic terminology used, and robotics becomes a very significant part of today's manufacturing activities. Though I have said robotics is in reference to manufacturing, it has several other areas of application. In fact, in almost every single area that you can think of, robotics has its place. Now, what I'll be doing in this session is create a preamble to automation in order to really understand what robotics is all about. So we need to understand a little bit of what automation is. Then I'll take you through to robotics, talk very briefly about how a robot is understood in terms of motion, in terms of forces, and so on, which we call the kinematics and dynamics. Then I have something to inform you about control systems, which actually makes the robot do things that we see in real time. And in order to do that, it uses several actuators and several sensors. So sensors, they sense an event, give a signal to the actuators start moving, the control systems take over, and we have a robot functioning. Subsequent to that, I'll take you through to maybe a little bit of smart robotics and mechatronics, flexible manufacturing systems, and some applications. Now, in order to be indeed inform all these areas of robotics in detail, it probably will not be possible. But I'll try and take you through of enough robotics that you understand what this is all about. So when I talk about preamble to automation, there are, at the central part, there are production system facilities. There's a product design, there's a manufacturing planning, there's manufacturing control, the business functions, and all these become functional with customer orders. That's a typical manufacturing area or manufacturing space. Now, when you come to the factory operations, you deal with design, you deal with manufacturing planning, manufacturing control, and their business functions. And on the periphery, you have computer-aided design, computer-aided manufacturing, you have computer-aided business systems, and you also have cost estimations, part planning, numerical control, and so on. Now, when we really look at the basic automation, there are three sub-areas of automation. You have fixed automation, you have programmable automation, and you also have flexible automation. And these depend on the quantity you produce and the variety you have in the production. So when we look at fixed automation, obviously it has very high production rate. Because it has inflexible design, the variety will be very small. And between the three, fixed automation costs the least. And this is an example for fixed automation. This is a fixed rotation bottle orienter. And many applications you must have maybe visited industry, process plants, and so on. So this is a fixed automation example where you can't change the automation. The entire shift, only this will be happening. The bottle will be oriented in the entire shift to a certain point. Now we look at programmable automation. Here, equipments are designed to accommodate the changes made in the system design. And this is useful, which means it has some capability of programming and changing the sequence of automation from fixed to something that's more flexible. So this is useful for batch production. It also has low production rates and is flexible with product design. So which means that you change the products and the design could be changed using programmable controllers and so on. Now this is programmable automation controller. There are several kits available in the market, which you program obviously to get at certain sequence of events, which gives you programmability into automation. So there is a significant growth that is forecast for up to 2024. The third is the flexible automation. Now here what we have is medium production rate, continuous production with variable design, which means you can keep changing the designs. High amount of flexibility is available, but the cost factor is also very, very high. Now this is the place where you have a lot of robots and robotics and several other automation devices and so on. That is how you get the requisite flexibility. Now we are looking at a flexible manufacturing center, which has several robots and so on. This is basically a continuous plant where different operations are carried out by different robots designed to do different activities or different sequence of events. Now, if you really look at relationship of fixed, programmable, and flexible automation, this succinctly captures what it is about. Now, if you look at the left side, you have fixed automation. You have very high, production volume, but very little variety, because you can't change the automation sequence that you have once set. And on the other end, you have programmable automation. You have a little more product variety, but the production capacity, the volume is fairly low. And flexible automation overlaps the two. So you have fairly great amount of flexibility which is built into the product variety, and you have fairly large production volumes, but this is all dependent on the kind of costing that would be there. So this is how a flexible manufacturing system appears. There is a robo, there is a robo controller, obviously, and there is a host computer. There is a machine station 1, machine station 2, and machine station n. There can be n number of machine stations. Now, having looked at the preamble for automation and looked at robotics or robos, which are used in a typical manufacturing environment, we look at what actually a robo is. So we probably believe that robo is a machine that looks and behaves like a human being, but they are actually defined, they are actually man-made mechanical systems where certain amount of intelligence is built into them, some programmability is built into them, and all this is done through a set of sensors, actuators, and so on. We'll look at all of them in a little time from now. So robotics is a science of designing or building an application of robos. Simply, robotics is study of robos. And they're used when speed is necessary, can work in hazardous, dangerous temperatures, like, for example, plasma welding or plasma cutting, or maybe in a nuclear reactor where fuel rods have to be changed, replaced, and so on. They can also do repetitive works, which are extremely difficult in terms of human adaptability. And then they work with the accuracy, which is absolutely repeatable over several cycles. Now, there is some history to robotics. The first, the Czech Republic playwright Karel Čapek first used the word robo, which means forced labor, and which means like a slave, working like a slave. And robotics was coined from robos and used in Runaround, a short story published in 1942 by Isaac Asimov. And the first robo was actually built in 1956 and was done by General Motors. There are 3 laws of robotics. There is 0th law: a robo may not injure humanity. So when we use robots, it should not injure human beings. A robo may not injure a human being or through inaction allow a human being to come to harm unless this would violate a higher order law. And the second law, a robo must obey orders given to it by human beings, except where such orders would conflict with the higher order laws. And there is a third law as well. It must protect its own existence as long as such protection does not conflict with the higher order laws. Now, entire robotics depends on these laws of robotics. Like I said, the first robo was created by Unimation. Joseph Engelberger, who was the first person to create a robo and very rightly called father of robotics. Now, Unimate was a company. It was used in General Motors, especially in die castings. It's a hazardous place where, cast material, which is extremely hot, will have to be removed from the die casting machine and so on. Now, this is how it looked like way back. And they are also used in several other areas for assembly of factory parts, handling, assembly, painting, surveillance, security, bomb disposal. Several robots are used in mine sweeping applications and for grass cutting, nursing, anything you talk about, an automated device can be designed to do that function, to have that function. So within robots, you have mobile robots, you have industrial robots, you have autonomous robots, remote control robots, and virtual robots. We'll see a little bit of each one of them. We'll also look at some details of where it makes a little sense. Now, mobile robots are obviously those which are able to move. Usually they perform they are of two types. One is a rolling robo, and the other one is a walking robo. A rolling robo obviously will have wheels and are controlled, and walking robots have robots on legs. So you have motion created by either rolling or through walking. Now here I have a rolling robo and I have a walking robo here. Now this walking robo, developed at Fraunhofer in Germany, it can walk even when one of its legs is injured. Now that's the extent of automation and intelligence built into these systems. We have several industrial robots. If you typically have an opportunity to look at Maruti automobile factory, you will see several industrial robots. Now here what I'll do is I'll take you through a small video. I may come out of the video before it finishes, but it shows you the extent of robots in a factory. Now this is a Mercedes-Benz factory, which shows you so you have seen the robots used in the Mercedes-Benz factory. In fact, every 10 minutes, they assemble one Mercedes vehicle. Now that's the kind of speeds that are possible. Now most of these robots perform repeated tasks, and of course they don't grow tired, and they don't have the labor laws applicable to them, things like that. So now, having looked at the automation as a preamble and having looked at some of the application area through a video, we'll now look at what actually is a robot. Now it obviously has a manipulator, or called as robo, main body of the robot. That has links, joints, and so on, which are actually the structural elements of the robot. Now, you can imagine your hand. There is a shoulder joint, there is an elbow joint, there is a wrist joint, and beyond the wrist, there is a hand. Now, you will also appreciate that if without the hand, whatever flexibility you have at the shoulder, or whatever degrees of freedom you have at the elbow, it's of no use. So there is an end effector, which is the hand, which is a device like the hand, which manipulates the objects and is a very important part of a robot. Now, obviously, there is energy required to make these joints move, make them translate, make them rotate, and so on. So therefore, you will need actuators. Now, actuators are like muscles of the manipulators. In a human hand, if I want to lift a bucket of 10 liters, if I have to lift a bucket of 5 liters or maybe 50 liters, the muscle power comes into operation. Therefore, in a robo as well, if I have to manipulate objects of different weights and so on, then I'll need actuators, which are typically the muscle of the manipulators. Now, they are typically pneumatic, they can be hydraulic, they can be DC motors, they can be servo motors, they can be stepper motors. So they can be either hydraulic, they can be either pneumatic, or they can be electric. Obviously, each one has its own plus and minus, its own advantages, its own limitations, and so on. Now, it's not enough if I have just muscle power. I need something to sense the motion, whether it's translational, rotational, whatever motion you have, something must sense it. And then that information should go to a central processor, and the central processor must take that data, analyze that data, and send back a signal to the actuator to maybe move back, front, right, left, whatever. So you have a structural element, you have an end effector, you have some actuators, and you have some sensors. Obviously, you need a controller, which is similar to the cerebellum in the brain. It controls and coordinates the motion of the actuators. Without a processor, you can't do anything. The brain processes. Therefore, a processor processes in a robot. A brain processes for the human being. Typically, it calculates things like displacements, velocities, accelerations of the robo joints, and so on. So how fast you want to move, how slow you want to move, or whether you want to move very fast and then very slow, and things like that. So this is a typical robo arm. You have an upper arm, you have wrist, you have joints, links, lower arm, all that. Now, obviously, when you talk of a robo, you have to describe what is degree of freedom. And in the number of independent coordinates you require to define motion is also the degree of freedom. So, for example, degree of freedom, 1 joint, 1 degree of freedom. So if you have 10 joints, you'll have 10 degrees of freedom. And in a simple robo, you have 3 degrees of freedom in the 3 mutually perpendicular directions, X, Y, and Z. A robo can technically have any number of degrees of freedom. And here I'll give you a small point to think about. Maybe at the end of the lecture, you can tell me how many degrees of freedom a human hand has. Now, the human hand also can have, the end effector can also have 3 motions, pitch, roll, and yaw. Pitching, these pitch, roll, and yaw are the 3 motions which happen about the 3 perpendicular axes. The terminology is similar to a ship in water. A ship can move, rotate about the vertical axis. It can rotate about the other 2 perpendicular axes, the horizontal axis and the one perpendicular to that. So you have the ship either pitching, either rolling about a horizontal axis, pitching, about the other perpendicular axis in the horizontal plane, and yawing about the vertical axis. Human arm can be used to demonstrate the degrees of freedom. Like I said, at the end of the class, maybe you can tell me how many degrees of freedom a human hand has. Now, typically, there are joints, there are rotary joints, there are linear joints, and so on. So there are prismatic joints, there are, rotary joint at the waist, at the elbow, there are linear joints, sliding joints, about the axial direction, and so on. A cylindrical robo will have both rotary as well as linear motion. For example, one rotary and two linear is a cylindrical robo. Now we need to really look at what is work envelope when we talk about robos. At the end effector, you take up, you notionally put a point at the end effector, and as the robo moves in all its possible positions, you draw the locus of that point on the end effector, and you create a work envelope. The work envelope is very necessary because it defines the extent to which the manipulator can be manipulated. There are many other dimensions to this, which I may not talk to you at this point of time because of paucity of time. You can actually relate them back to a human body, a human hand, and talk about the work volume and so on, work envelope and so on. There are also points, like for example, on a human hand, on a finger, assume there is a point, and you try and draw the locus of the point by moving your hand in all possible directions. And the volume that you create is the work volume of the human being. Now, having said that, there is another question. Is it possible that you can reach any point within the work volume by the end effector? The answer is a no, and those points are actually the singularities in the system. There is a classification possible: Cartesian, cylindrical, spherical, depending on the coordinate systems that we are using. The most familiar is a Cartesian, where three linear motions about x, y, z happen, and they need three prismatic joints, and most of the time they're used as pick and place robos. So this is how Cartesian robo applications happen. Now we have a cylindrical coordinate frame. Obviously, there is one rotation and two prismatic joints, and therefore think about what the work volume would be here. These are cylindrical robo applications used extensively in DNA screening, drug development, toxicology, and so on. We also have spherical polar coordinate systems, spherical or polar coordinate systems. And they have spot, gas, and arc welding applications, reaching horizontal or inclined tunnels, etc. Much more flexibility is available. And the robo sometimes is also known as the gun turret, where if you have seen military vehicles where there is a turret mounted on the vehicle and which goes around shooting in the direction in which it is pointing. So these are all spherical polar coordinate systems. Now these are used extensively in the car manufacturing industry and welding. The next one, which is extremely important, is a Scara robo, selective compliance assembly robo arm. And this was developed for most of the time planar operations on a plane. Fast movement with light payloads, rapid placements, Typically, PCB assemblies, PCB welding can all be done through this. So these are Scara applications, like I said, mostly on a plane. Then we have the Revolute Robo or Puma. It's a company again. It resembles a human arm. The robo rotates much like the human waist. And this is ideal for spray painting, which is a very hazardous application. The paint stays in the air and you breathe that, and people are, they can get medical problems like asthma and so on. So robos are used for spray painting and welding, which is also very, very hazardous. And they mimic human motion, human movements. So these are Revolute applications: spray painting, metal, inert gas, MIG welding, TIG welding. They're all done using these robos. Now we come to humanoid robo. This was developed as a recreational and entertainment value, but today it has much more value in terms of creating addressing household chores and acting as aid for elderly people. It can open a refrigerator door, or it can bring out a glass. It can things like that. Now, like I said in the beginning, it's extremely important to know that without a hand, without the fingers, the portion below the wrist, the hand has really no meaning, no value. So therefore, the fingers, the portion below the wrist is extremely, extremely important. What you see here is a robotic hand, which is extremely highly evolved. But in a very simplistic sense, you have a hand that is attached to the end of the robo, or called as an end effector. Now this is the hand. It's used for grasping, drilling, painting, welding, anything that you think about. So ideally what would happen is, if I change the application, the end effector would change. So it simply means that. So therefore but relating it back to a human being, you do a variety of activities with a single hand, and you have two of them. In fact, for a human being, you have 2 eyes, 2 ears, everything is, there is a redundancy built into the system. But if you want to really automate that, it's extremely, extremely difficult. In fact, the hand is also extremely dexterous, and that's a property which is extremely difficult to build into a mechanical system. But today we have technology to do all that. Now, end effectors can be tools, they can be grippers, mechanical, magnetic, pneumatic, hydraulic, electro-pneumatic, electro-hydraulic, pneumo-hydraulic, anything is possible. 2-fingered is most common. We have 5 fingers for a human being. If you really think about it, most of the jobs you can do with 2 fingers. A 2-fingered, most common, and in a mechanical sense, and multi-finger end effector is also available. It applies force that causes enough friction between objects. In fact, without friction, you can't even walk. You can't ride. A mechanical system as well. You need friction to hold objects between end effectors. It's some objects which may be delicate, brittle, but there are force sensors which take care of those kind of events. You take end effectors, you can have pneumatic effectors, suction cups. If you have a flat plate on the floor, you can suck it up and things like that. So depending on the application, you have to design what kind of end effector can do the job. Now, having looked at some basics of what a robo would have, you all must have also seen movies like Jurassic Park and so on. So this is probably a very de-glamorized approach to robotics. When I say that it has joints, it has links, it is based on a Cartesian coordinate system, or is a Scara based system, and things like that. But that's what it is. We can build more complex systems, but you begin here. And in order to understand all this, in order to understand the motions, the forces, and things like that, you need to really look at what is kinematics and what is dynamics. I'm not going to go through the detailing of this, but very simply put, kinematic model studies the motion of the robot regardless of force and torque. Don't talk about force, don't talk about torque, just talk about the motion, and that is kinematics. And you use Dinavish, Hartenberg notations for this. And it's very, very essential for describing an end effector position. Where will the end effector go? If I move the waist so much, if I move the shoulder so much, if I move the elbow so much, if I move the wrist so much, where will my end effector be in reference to my initial position? That motion is defined by a kinematic model. Once I define the kinematic model, then I can study the relationship between the joint actuator torques and the resulting motion. Obviously, motion is not motion should have certain torque built into it. I know what load I have to here I use Lagrangian method and synthesizing the dynamic behavior. So, having looked at some of what basics of is, what is a preamble in which robotics work, now we look at some control systems. How do we control these actuators and things? I'll come back to actuators a little later. Now, I have essentially three systems. I have an open loop control system, I have a closed loop control system, and I have a adaptive control system. In very simply put, open loop control system does not have feedback. A closed loop control will measure the output and compare with what I require, find out what the error is. That error is added to the input, and then over the next cycle, the error becomes smaller and smaller, and somewhere probably it may converge. And in a system, every single element has a feedback loop, and therefore the convergence is much faster in an active system. So we don't go into more of systems at this point of time. There are various devices used. There are linear encoders used for measuring small displacements. There are encoders used for rotational motion, and so on. And there is also a proportional control. There is a differential control. There's an integral control, which is also used in order to control the systems. Now this is so I have skipped some part of that control systems, but in short, what you need to really understand is when an actuator, I program the motor to give 20 degrees, but I do not know really 1 to 20. So use an encoder, measure what it has, and the actual measurement says that it's 21 degrees. So there is an overshoot of 1 degree. So that 1 degree comes back to the input, and the second cycle starts. So the error in the second iteration becomes maybe 0.5 degrees, like that. And this continues to happen until whatever is the precision and whatever is the accuracies and things like that. Beyond, we have autonomous robots which are self-supporting. So we are going into a little more complex systems now. They run programs that give them opportunity to decide on the action to perform, and so on. So they work by themselves, is an autonomous Remote controlled robots. We have very complex tasks like you have a nuclear reactor. You can't go anywhere near because of radioactivity. So you have a robot inside the reactor separating the spent fuel because job of removing the spent fuel from the reactor and replacing with new reactor. Now, when you want to do this, you have to actually have another robo outside the reactor, and you start moving that robo, which is outside the radioactivity zone. And whatever you do with that robo will be faithfully reflected inside the reactor. So these are teleoperated robots, and there are all those complex systems available. There are also systems available for space missions, robots in the Antarctic exploring volcanoes. There is underwater exploration. For every application, obviously the design will be different. The parameters will be different. The principles will be similar. So this is what is robotics I spoke to. So I won't go into details of trying to understand what robotics is about. Now this is a frame which is being dropped by complete programming, and these are all teleoperated systems. Now I will take you to a little about sensors and actuators, because that's an extremely important part of robotics. Now, this is actually Heshing Wang, from a professor from now what this tells you is about several sensors. Sensors, obviously, you need to measure parameters which you use to make decisions, depending on what the value of those measurement is about, or measuring is about. So you have position, you can measure position, orientation, acceleration, distance, size, force, moment, temperature, luminance, weight, everything you can measure. So you have ultrasonic sensors and sensors. Now this is a figure which will tell you there are different sensors available which are used in robotics to measure different parameters. And each one has a different input-output relationship, different way of behavior, different technically defined parameters. So therefore, you will really need to choose the right sensor for the right application, and that is the crux of the problem. There are internal sensors, optical encoders. There, like I said, the angular motions, acceleration sensors. If you want to measure the acceleration and so on. If you want to measure the velocity, there are velocity sensors and so on. External sensors, you have cameras, you have range sensors in order to find out how, at what distance the object is. There are infrared sensors, there are laser range sensors, ultrasonic sensors, proximity sensors, photodiodes, force sensors, basically strain gauges, and so on. So you can measure position. This is the optical encoder. This is the principle on which they function. And you have potentiometers with varying resistances as you change the distance. So you can measure the distance. Once you measure the distance, the first derivative will give you the velocity. The second derivative will give you the accelerations. We also have inertial sensors, gyroscopes, in order to, gyroscope is, if you really want to understand this, if you have motion about two perpendicular directions, a motion can happen around the third perpendicular direction, and that motion will have to be countered if the body has to be stable. Now, in a two-wheeler, the human being himself functions as a gyroscope. In a four-wheeler, you don't need a gyroscope because the road is not flexible. But in a ship or in an aeroplane, you need a gyroscope, and many of these things are used in robotics as well. So there are several applications of gyroscopes. then you measure accelerometers, you measure tension of a string, you measure deflection of a beam, you measure vibrating frequency of a mass, and an accelerometer. You can actually measure accelerometers at several applications. You can even measure the earthquake intensities and things like that. So there are 4 sensors based on Wheatstone bridge. There are torque sensors, there are range sensors, there are IR infrared sensors, and so on. Then there are flight range sensors. This is a principle on which these things work. And here I would want you to look at there are also touch sensors, the tactile sensors, which behave on change in pressure, which is measured, and so on. Now we come to robo actuators. Now here what I have is, again, like I said, you have electrical actuators, you have hydraulic actuators, you have pneumatic actuators, and so on. The pneumatic systems, positional accuracy is difficult. In hydraulic systems, positional accuracies can be very, very high. And you have electrical actuators like motor, DC motors, and things like that. Now I'll quit from here. This is the hydraulic actuation. This is the pneumatic actuation. And these are the electrical actuators, which are, they have several advantages over pneumatic and hydraulic devices. Now, I will quit from here and go back to smart robotics and mechatronics. You have seen a little bit of what is happening in most of the robotics. Actuators is very important to give the motive power. The sensors are important to measure that motion, displacement, velocities, accelerations, and some of the forces as well. So there are medical robotics which function at the nanoscale. Nanoscale is 10⁻⁹ of a meter. And here I have 2-3 examples of it. When an implantation of a tiny robo into our bloodstream, the robot detects the cause of the fever, travels to the appropriate system, and provides a dose of medication. These are all very small robots, which are called nano robots. They also treat conditions like arteriosclerosis, physically chipping away the plaque along artery walls. And there are also nanorobotics which carry small ultrasonic signal generators to deliver frequencies which directly attack the kidney stones and break them. So these are some of the, and this is the level of robotics in medicine, or medical robotics as we call them. Oral, manual, cooperative manipulators, teleoperation, autonomous, everything is used in medical robotics. We also have virtual. These don't exist in real life. They are basically programs, building blocks of software, sitting inside a computer, but they can simulate the real robots. And search engines use such kind of robots. For example, if you go to Google and type any keyword, you get a reply back saying that 0.23 seconds, and you get a whole lot of data. And that is basically done by virtual robots and several other algorithms based on AI and so on. Now, obviously, there are several advantages. You can go to planets, you can visit planets, you can go underwater, undersea, you can get information that humans can't get, work 24/7, perform much faster tasks that humans possibly cannot do, and many of them are very, very flexible. And there are obviously some disadvantages as well. People can possibly lose jobs. It needs power, and it needs maintenance, and it needs a lot of money to buy and maintain a robot. Now, in a typical work environment, we have what we call as flexible manufacturing systems, where typically robots are used, which I have actually shown you a video of Mercedes-Benz, which I have come back again, is a flexible manufacturing system. They all typically look like this, and they are completely automated plants. And today we are in the Industry 4.0 scenario. We are in a scene where either we compete and provide the quality that the global world seeks, or we are out of business. So therefore, these are some of the things which we really need to worry about now. These are typically those manufacturing systems that we're talking about, this well factory and so on. I won't, finally, I'll show a few applications of robots where you will get an idea of how evolved the field of robotics is. Now, this is an android which is actually just 9 inches tall and 2.2 inches in wide. And a great accomplishment for one person because the legs have 6 degrees of freedom and the head has 2 degrees of freedom. Now, this is, in typical human terms, it's a very, very important breakthrough. Now, some interesting applications are this is designed for exploration. You know, it entered the active Mount volcano and looked at what kind of conditions exist there. This is a musician robot. It can play piano. This is a robot with multiple legs. Several servo motors are used and so on. It's actually a hexapod. Now here we have a motion control of a dance partner robot in cooperation with a human being. Actually, you can do the gait analysis. You can find out actually how a human being walks, build a robot, build that gait analysis into the robot, and the robot will actually start dancing like a human being dances. Now here I have systems floating on water and so on. So there are several applications. These are industrial applications now. You know, this is a palletizer for in a food industry where potatoes are packed or vegetables are packed in plastic bags and so on. This is a washing detergent washing machine robot and so on. This is a painting robot. This is a TIG welding robot. This is a multifunctional robot for die casting machine. I just wanted to, there is one. Yeah, this is plasma coating with robots. This is a very, very highly hazardous operation where you will need plasma coating and very harsh workings. This is again a painting robot and so on. So I leave it at this. The last 2 slides, they just tell you the future of robotics is everywhere. And with AI, you build a lot of intelligence into a robot and they can do functions which we probably as human beings will not be able to do. Now, in order to demonstrate advances in research and stimulate science, we have RoboCup soccer competition, which many of you may be aware of. And there are several goals set and different algorithms are built by people to solve the problems. And in future, we also have Industry 4.0, which is coming in, and a lot of robotics which operates those kind of machines. In fact, Industry 4.0, machines talk to machines, humans talk to machines, machines talk to humans, and machines also can talk to machines. Now that is all possible only by a lot of artificial intelligence built into the systems. So this is where I stop. Thank you so much. And if there are questions, I'll take them. Thank you.
Well, thank you, Dr. Mantha, for such a wonderful session.
Yeah, thank you.
The session was indeed very, very informative. And I'm sure all participants to have some valuable takeaways from the session. So, sir, you permit, I mean, we can take few questions.
Yeah, sure.
All right. So there are many questions in the QA panel which has come up from the participants. So I'll just take this one. This probably would have come from a student. Is it necessary to have mechanical engineering background to learn robotics?
Yeah, I mean, robotics is an interdisciplinary area. So it can be studied by mechanical, by computer science guys, the electronics people. In fact, robotics has about 30% of mechanical engineering, about 30% of electronics, and 30% of computers, computing science and communication. And the remaining 10% would actually be the applications which define the systems and so on. So it's an area which every person with a certain specialization would want to do, but the research that he would probably do would be in his area as applied to robotics.
All right, sir. Thank you. Okay, here is one more question. How the robots will analyze in health sector that a person is properly recovered or not? I think this is asked in context of the current COVID situation, where a lot of robots are being used to help the patients.
No, the present every automation solution is not a robot. We must understand that there are the cost to effectiveness ratio also must be looked at. And in medical robotics, obviously, medical robotics is very evolved, and remote surgeries are also done, and assisted surgeries are done. In terms of COVID and so on, the requirements are very, very different. Obviously, there is a testing that will first of all estimate whether a person is infected or not. Once that is done, there are very limited options because there is no active vaccination that is available, active medicine that is available. But within the medical application, it could be possible that a few patients end up in ICUs and so on, and at those places facilitate the because of the nature of the patient, basically is infected. So therefore, you can certainly have certain specially designed systems to handle the equipment around the patient. Now there is a process called intubation and extubation where certain operations are carried out with the patient, and those could require a lot of assisted systems.
All right,
yeah.
Thank you. This one, what is the scope of a BTech course in robotics and automation? I don't know, probably this has come from an academician or a student.
No, robotics is a specialization, and there is a lot of background that is required in order to understand robotics and that up as a career. I mean, it's a different thing to go through a 1 hour lecture on robotics and try doing something. So it's very necessary that there is a certain background that is built. So therefore, you need to understand mechanical engineering principles, you need to understand electronics, you need to understand computer science, you need to understand communication, and so on. So a BTech in any of these areas, and then a specialization maybe in the final year, going through 2 semesters of robotics would certainly help. Or maybe a pure mechanical engineering background with a postgraduate degree in robotics would make that the problem so much easier to understand and apply in terms of real-time applications.
All right, sir. We'll take this last question.
Yeah.
Where do you see the future of robotics in defense in India?
Even today, future certainly is I mean, there is a lot for the future. But even today, several systems are already automated, and robots are used in military applications and so on. I had shown you one slide where you know, a lot of pre-programming allows a certain missile to be dropped at a certain point, predefined point, and things like that. And there are also controlled launch systems. There are guided vehicles. There are vehicle-mounted guns which are controlled remotely. There are minesweepers. There are all kinds of applications. Anything in the warfare today has a certain amount of automation, and the more complex systems which are remotely operated, they are all basically robotic systems.
Fine. Thank you, Professor, for answering these questions. So it was a very nice session today, and we would like to thank from the bottom of our heart for your time and your energy today you spent with us. Thank you so much, sir.
Yeah.
Okay. Queries we are done with. So to be prepared is the half victory. Our STAR Robotics Expert Program will help you to take off your career with confidence and skills in the automation age. For our audience, if you have any unanswered question today, you can post it at query@starcertification.org. In fact, you can also write to us to know more about our certification program, offerings, and corporate batches. For the latest updates, webinars,